right. Well, thank you everyone for attending today. Today, we're going to be having Dr. Ali Nafchi talking about precision agriculture and sustainability. And so Dr. Nafchi is relatively new to SDSU, and we're excited to have him here. So Dr. Nafchi, I'll pass things over to you.
Hi, good morning, everyone. I am Ali Nafchi. I am with Plant Science and Agricultural Biological Engineering Department. Today, we are going to discuss how precision ag concepts can improve ag sustainability and farm profits. So I'll go a little bit with precision ag background, and I can simplify it as it's all about management. And during this management, we use crop, soil, environmental information, and advanced technologies to and computer interface to perform 5 R's in our field. We want to perform right input, right amount, right place, right time, and in right manner. So variation in a field.
Sorry to interrupt. If you have you want to put your slides up, go ahead and share those.
You don't have them?
Nope, we don't see those right now.
What happened was when the intro slides started playing, your slides stopped sharing. So I think you're going to have to hit share screen again.
Okay. So do you have them now?
Oh, yeah. Yeah, we can see them now.
So this is right the screen. Is this right the screen?
Yep, you're all set now.
Yep.
All right. Sorry about that. So I'll go with precision agriculture background. It's all about management. We are going to use soil, crop, environmental data, and with using advanced technology and computer interface to perform 5 R's. And these 5 R's are right input, right amount, right place, right time, and right manner. So variation in field result, tremendous amount of variability in yield. So all crop input, fertilizer, irrigation, seeding rate, etc. were the same for these 2 locations of a 10 acres field. However, the yield was 4 times more in the area with heavier soil texture in the left picture. So when we have variation in soil properties, which cause variation in water holding capacity, infiltration rate, and soil nutrients availability, precision ag can help to address these variation by applying those 5 R's. So something to consider is optimum use of input does not mean minimizing them. Of course, we want to apply less amount of chemical or fertilizers, but it does not mean optimization means minimizing them. So optimization is working with higher percentage of the capacity or efficiency of the system. And with optimum level of input, we will get higher efficiency or capacity. In this picture, you will see the law of the minimum diagram. Only you will have one limiting factor that limit your yield or production. If you have one deficient factor, which could be nutrient or other factors, temperature, water. If you have one factor limiting your production, even if you apply more than sufficient of all other inputs, you cannot improve your yield. So you have to address that limiting factor. First of all, you have to find that limiting factor, and by working on that limiting factor, you can improve your yield. Another point to consider is for a 300 bushel corn yield, you need proportion level of nutrient available to plant for that 300 bushel of corn. So in other words is, higher yield takes more fertilizer, but it does not mean, again, you have to go and apply more fertilizer. You have to go and find that limiting factor first. And that limiting factor would not, are not only elements related to nitrogen, phosphate, and potassium. You can find other, maybe one limiting factor would be boron or other factors which we have to find. So in this slide, we want to talk about the R's, the right input, right amount, or right timing. When we apply, this is just for nitrogen, for example, when we apply nitrogen, the 100% of nitrogen application we apply, we have only 50% nitrogen use efficiency. And if we do it right, we may be able to improve this nitrogen use efficiency. For the timing, the percentage we use up to V6 from the planting to V6 would be only 5%. And imagine if you apply 100% of your nitrogen at planting and something happened here between V6 and V10, for example, which we reached to 25% of usage of nitrogen. If we have heavy rain here, what will happen to your nitrogen? And so the point is the recommendation for nitrogen application based on the precision application is to apply a started percentage. You can go with 25% or 30%, or some people, they use 50% at planting, and then between V6 to V8, maximum to V9, you can apply more to get you to the maturity level. Another topic we want to talk here on this slide is the method of application. Again, if you apply your nitrogen in middle of these two rows and you get heavy rain, what will happen to your nitrogen? Depends on your soil type. If it is sandy soil, it would be washed away and you will have lots of leaching. So we have wide drop system that can be another option. We are going to test these two methods to see which one would work better for us. So the data and information we are using in Precision Ag are related to soil data, which related to the type, nutrient requirements, nutrient availability, farm data, the weather data, and also data related to topography are important. Crop data, if we have some pest infestation, do we have any outbreak from which we can point it, which is starting from certain area? Those are the important information we can use to improve our farm performance. Yield data, very good indicator, but very tricky. So the recommendations sometimes are, okay, average 10 years yield data. We will discuss these topics. All of these information can be used to make important decisions. Goals. So I would say the goal is to increase sustainability and, of course, the profits. But during this process, we would increase the production efficiency. By doing that, we increase the sustainability and profit, improve product quality. Imagine if we have lack of, for example, nitrogen or some other elements for our wheat production, it would cause the lower protein in wheat, and that would reduce the quality of our product. Reduce chemical use. We don't want to consume nitrogen. This is obvious. Energy efficiency, of course, when we don't use excessive amount of fertilizers or other chemical, which we spend energy to make them, that would help for energy efficiency. Also, when we practice no-till or minimum till, we are improving the energy efficiency in our agricultural production. And with all of that, improve environmental qualities. If we use less chemical, higher energy efficiency, so obviously will improve environmental qualities. Management zone philosophy, we are going to talk, which is managing each crop production inputs like fertilizer, lime, tillage, irrigation, and other inputs on a site-specific basis by subdividing a production field into smaller units called zones and managing each unit or zone separately. So primary steps for precision agriculture to get to precision agriculture practice are first to find and identify the variations, second, create different zones, and finally, third, to treat each zone individually. So yield and soil data, nutrient requirements, pest, infestation data, weather forecast, and all other information can be used to perform zone management. In this process, we use computer interface sensors with GPS, and the gathered information would stamp to their location. So later we can say for this area we had this phenomena or observation. So how to identify the soil variation and create zones? Aerial imagery, soil electrical conductivity, soil sampling, yield maps, and soil survey provided by USDA, which is free of charge, can be used for creating the zones. And I'm going to explain these methods. So electrical conductivity. Soil electrical conductivity described as ability of soil particles to transmit an electrical current. So the unit for this electrical conductivity is millisiemens per meter. And if you have closer particles and finer particles, they can take the electrons, and if you have higher electrolytes, take more electrons and transmit it from point A to point B, which described as electrical conductivity. And these phenomena or these measurements, soil EC, can be used to quantify the soil texture. We make correlation between the EC readings and soil texture. And based on that, we can have yield potential and assess the production efficiency or performance. Because the soil texture is static, what does that mean? It means over time, it would not change, rapidly. So we will, if we don't do major change, and if we don't have major change, the EC maps are sometimes valid up to 7 years, depends on, of course, the soil type and conditions. But if we do some major change, so that EC would change. We have two types of EC machines. One is contact sensor, another is non-contact sensor. This is contact sensor with coulters. And we have 6 coulters here. With 2 and 5, here the coulters 2 and 5, we send electrical current and we read them on 3 and 4. And the question is, then why do we need 1 and 6? So the traveling depth of the electrical current would be function of the distance from the two coulters we have the electrical current. So it means the distance between the coulters when it's 9 inches, the depth of reading would be 1.4 of that distance. So in other words, we will have a reading or shallow readings of 12 inches, which is the topsoil or the root zone. And we will have another reading, which is 3 times of the shallow readings, which is deep signal, and it would be 3 times of 12 inches would be 36 inches. So we have 2 types of readings, shallow and deep readings. So what's the use of deep readings? First of all, we can compare the topsoil with the bottom soil, the deep soil. And excuse me, if we have problem on water infiltration with deep EC, we can check them, we can see them. Another machine is non-contact sensor, and non-contact sensor with no contact to the soil, sending electromagnetic wave into soil, and from there we measure the EC. The collected data from these 2 machines are similar. We have same, deep and shallow readings, and from both we can have the, topsoil reading and shallow readings, which is related, could be related to infiltration conditions. And so we are going to test these 2 machines, and I will give you update on the performance of these 2 for South Dakota farms. But one thing I can say, if you have rocky, field or soil, and if you go so fast, by hitting the rock, it would jump to the air, and while you're traveling, the disc or coulters are on air and not contacting with soil, and you will get bunch of reading zeros there, and it would average it down. That's why we may, if based on condition, we may get different performance. So the finer particles of clay conduct more electricity than the coarser silt or sand particles. So if we have higher percentage of clay, it means we will get higher EC reading. And if we have higher percentage of sand, we will get lower EC reading. And it's not only because of the finer or coarser particles, but also it's related to the electrolytes or salinity we have in clay, more salinity or electrolytes we have in clay soil that can carry more electrons and can have higher conductivity from point A to point B. And for sandy soil, it's obvious because of it washed all the electrolytes, you will get lower electrical conductivity. This is product of the electromagnetic sensor. I tested with the various machine which that was contact sensor, and the result, the product are the same. Something I want to mention here for deep EC and shallow EC, we see differences between deep EC and shallow EC, deep EC and shallow EC. And there would be some reason, and we want to find out if it was not there and we have it now. So we have to find, maybe it was blocked drainage and now it's open. That's why we get lower EC, it washed all the electrolytes. Or maybe we compacted the soil here, or maybe we added some organic matter. There would be a reason. So based on what I said, we can reassess our performance by doing over and over this EC and measuring the EC, and we can find the problem area. So another method to create zone is soil sampling. And we can use two methods, which are grade sampling and management zone soil sampling. So for grade sampling, we will uniformly divide the field into grades, and we'll go and collect sample from the grades, which would be 2.5 to 10 acres size. And there would be procedure, we'll talk about it a little bit. And we have also the method of management zone soil sampling. So I want to talk about the grid sampling. Here in this grid, we have gray, blue, pink, yellow, and green. And so the question is, based on the procedure we had for soil sampling, we are going to sample, let's say, 10 samples from this grid, mix it together, and send it to lab. What you'll get from the lab, the result you'll get from the lab are representing which part of your grid. It would be average of a scaling up or a scaling down of numbers, and which is not showing or representing any soil type here in your grid. It would average it. On the other hand, we will have management zone sampling, which you can go and create your zones. Of course, it would not be very accurate. For that reason, maybe for the border, you can have some more samples around the border of the zones, and to check where you will have these zones or the lines of the zones. First, based on one phenomena, can be yield data, can be EC mapping, or other information or aerial imagery. You will go and collect samples from your zones and mix those zones together only, not in the grid. So another method is yield data. So yield data are really good. Everybody talks about them. But imagine yield data of this year would entirely change for next year. Means so you will get some result this year, and next year you will get different result. And if you cannot find interpretation of the why this happened, then maybe you'll end up to averaging the yield data, which is not really good idea. I want to talk about 2 years of yield data, 2021 as a dry year and 2019 a wet year. This is same field and same crop. So if you look at the corner of this field, in 2019, which was a wet year, you had low yield here. In 2021, which was dry year, high yield. What caused this? We have to find out. This would be one point or one zone for you to go and collect samples. So you want to have samples from here and here to find out what's going on. And so just, some assumption, we can say, because we had maybe problem with infiltration rate or drainage and toxic electrolytes, we had lower yield here. And because we trapped the water on 21, it would provide it back to plants, so we had higher yield here. Could be. But we can go and sample, and we can confirm it and do validation and calibrate even our reading or observations. Some other area, similar area, we have the same situation. We need to sample from these two locations. So maybe we want to, mix the samples, or simply we can just send it to for test. And we have samples from here, and test it, what's going on. Some other area, you will find no matter what, if it is dry year or wet year, you will get high yield or good yield. This is also the area you want to consider it as a zone, and you want to have sample. You want to find out where the majority or the money you are making or profit you are making on your field coming from. By targeting those areas, you want to improve your yield, because those areas you are actually making higher profit has potential to increase your yield. And I will get to some area which, no matter what, if it is wet year, dry year, you are not making money or profit. So the point is, if you are losing money, you want to consider here that should I reduce my inputs? And by reducing my inputs, I may be able to make it break even, because I don't want to leave it unplanted. Or so I can do something about it. And if there is some problem, or there are some problems there that you can work on them by soil sampling. Again, for these areas also, you want to consider them as a zone and soil sample them and work on them. Maybe by adding cover crops or organic matter, or sometimes it could be related to some deficiencies, but we can find out. You can find out and work on them. Some other area which are not marginal area, maybe you are not losing money, but not high profit. Those are also another zone to consider and check them. So these are yield data. What I want to emphasize here, we don't want to average the yield data. We want to actually categorize the years. We want to classify them. We want to say this is dry year, normal year, and wet year. If we want to go, deeper, very dry, normal, wet, and very wet. And later, when you want to use or call for the information, you will compare apple with apple. You don't want to have average of all to become all normal, and so you don't get anywhere. So apple with apple, dry year with dry year, wet year with wet year. If we do it this way, the yield monitoring and yield maps are really a good source for soil sampling to create zones. The good news here is the aerial imagery, EC data, and yield data, if we do them right, have really good correlation, and we can use any one of them and it will give you idea about your field condition. And by adding the benchmarks to your historic data, later you can refine this information. So takeaway, data and information management. So we want to collect data as much as we can from our field, and we want to organize them. We want to categorize them, classify them, validate them, and calibrate them if needed. And when we want to do farm planning, we want to compare apple with apple. If we are on a wet year, we want to just compare it with the wet year, not average of 10 years. And by doing that, we can analyze it and add to the archiving data. So now, let's say we have all the information and a different zone created. Now what? Now we need automation and controlling system to implement the Precision Ag recommendations. Not all of our fields are very nicely rectangular or square shape, if any. So when we have fields with irregular shape, and so we have obstacles, waterways, and definitely we will end up some area having overlapped or unplanted. Today, we have single unit automatic control or to control units individually. And also we have automatic section control, which can help to avoid planting with overlaps. On the other hand, variable rate technologies would help optimizing our operation. I have this animation here. The color-coded numbers are inputs, and the map is the prescription map. So if I play this one, you will see for some area, it will change the color of the application, which would be the inputs, and some area, it does not apply anything. So we have a lot of innovative and supporting technologies in agriculture today. With the GPS technology like auto steer and guidance system, which is revolutionary tool in precision agriculture. We have wireless communication system to synchronize our operation, and variable rate technologies allow farmers to farm more accurately, leading to higher trends and higher profits. So variable rate irrigation, much like auto section control on previous slides, on conventional irrigation system, we may have some problems such as center pivot overlaps or causing too much water to be applied on overlapping area, problem with off-target spray leading to water or waste the water for the roads. With precision or variable rate irrigation system, we can address the variations in field. So we have this animation. We don't want to irrigate the roads, we don't want to irrigate the pond, and we want to change the rate while we are moving from different soil types, for example, or some puggy area, some even if we have different crops, we can address that with different water need. Another system related to precision ag, if you have irrigation system or precision irrigation system, you can use precision nitrogen fertigation or nutrient fertigation. And with this system, you can apply irregular amount of application regardless of how much water you want to apply if you have separated fertigation system. For example, if you want to apply 1 inch of water for entire field, still you can change the nitrogen fertigation to apply different rate on uniform application of irrigation system if you have separated fertigation system. So implementing variable seeding rate. By now, we know precision agriculture is a concept of farm management that utilize observations of measurable variabilities on a farm. And optimum level of inputs are defined to reduce negative environmental impact while maximizing profits. For example, we need to implement variable seeding rate and adjust the rate recommendations by seed companies for our condition and practice management. We use the yield data to create zones, but still sometimes we want to check these recommendations by companies are good for my practice or not. Maybe my situation is different, so I want to make sure I am doing it right based on the recommendation. This is one project. The recommendation was this for the field. Usually, the grower was applying the flat rate with this recommendation. When we create zones and we apply different rate, and with different rate, we got higher yield. This is what we want to see. We want to see with reducing the input, we actually improve or increase the yield. Of course, we have to repeat this one. This is only 1 year, but when we do the replications, we will come up with idea how my practice or my management would change the recommendations by seed companies or scientists even. So another point is any other chemical or any other input application I am working on or operation I have, I can ask myself, can I do it variable rate? And then why, how? And we are here to help you if you consider you have some application and your field does not need that application, especially so now you know for pesticide or chemical application, spraying chemicals, yeah, you can use variable rate, but for all other applications, for drainage, for even manure application, so we can help. Managing soil compaction and variable depth tillage. So nationwide, farmers across the US lose over $1 billion in crop revenue every year due to the effect of soil compaction. So hard pan is a dense layer of soil, usually found below the topsoil. And there are different types of hard pan or compaction level. But generally, they reduce the water infiltration and root growth. So if compaction exists, we need to do something about it. The questions about managing soil compaction we have to ask is how to identify the soil compaction problems. And do I need tillage or deep tillage? How deep should I go? And where is the required in my field? Do I need it entire field or some area? Is annual subsoiling required? So that's not too easy to detect the hard pan, to find when and where we have it. What makes it too hard to detect is the hard pan depth and thickness in a field is not constant and does not exist all over the field. Therefore, we need a device to detect this. So how to identify compaction problems? We have reduced water infiltration, uneven stand, shallow roots, penetrometer, we'll discuss this. So reduce water infiltration. Sometimes you've seen this picture, water standing in your field, sometimes cause denitrification. This is reducing the water infiltration. And we will have uneven stand, some area of your field growing faster. Shallow roots, if you compare the roots, some of the plants or crops are having shallower roots. And we have a device called cone penetrometer. With this penetrometer or device, you can actually quantify and measure the cone index, which is representing the soil strength. And if you don't have this device, if you have a half-inch rod and sharpen the tip like a cone with 30-degree angle and have a handle on top of that with your weight, which I assume, with 200 pounds of weight, easily you should be able to push it into soil. And if you cannot push it into soil, it means you can think and you can have soil sample to measure the soil compaction. If you have soil compaction or with higher soil cone index or soil strength, the soybean yield would reduce, the root length would reduce. And if compaction exists, then tillage or other mitigation is needed to rupture the compacted layer from optimum to have optimum performance of crop. And mitigation means we will talk about cover crops. Easily we can use cover crops to improve or reduce the compaction, improve the soil health related to compaction. If the cone index or soil strength is below 300 psi, the tillage you need is 0. But if you are above 300 psi here, you may need to do something about it. As I mentioned, maybe you can use cover crops. Cover crops is not only, we are talking about the tillage radish, not only rupturing just by growing into the hard pan, but also by just adding the organic matter, it would break it or improve the soil health or reduce the importance of or negative impact of the hard pan. So this is a 40 acres field, and as you can see, 52% of whole field does not need any tillage, and only 20% needs deep tillage and 28%. So in other words, even if you need to use tillage, you don't need to use it for entire field. For managing soil compaction, as I mentioned, we needed to detect the depth as well as the thickness of the hard pan. So we designed this instrumented shank. We have local on it, and we drag this one shank into soil. And with these readings, we will get the thickness and the depth of the hard pan. And we had another part here adjusting depth system. With this system, we could adjust the depth to do on-the-go variable depth tillage. So with this system, we reduce the fuel consumption by 45% with no reduction in the yield. So we have ongoing projects here related to precision ag. We have precision cover cropping system funded by USDA and NRCS that we are working with farmers, and we would like to promote this. We have a wide drop system. We want to design a system to wide drop and interseed. But the point is we wanted to have it very inexpensive so farmers can afford it. We have another project, which is nitrogen and sulfur biosensor and artificial intelligence, which we consider as a future of nutrient management. We are working on this project as well. And I want to explain this project. If you are familiar with nitrogen-rich spot, so you apply nitrogen-rich strip. If you are familiar with nitrogen-rich strip, this is similar to that one. In a state of that strip, we will have spots. The problem with nitrogen-rich strips, you cannot find all good spots or good strips to apply nitrogen sufficient in your field. So how it works, when you plant your field, you will go back and have one strip of enough nitrogen or enough nutrient to later, at the time of side dress, you want to go back and compare that strip which you apply, you establish there, you want to compare it with sensor. Okay, I applied this much nitrogen for my strip, I read the reading from the field, and I compare these two numbers, and based on these numbers, I'm going to apply this level of nitrogen. The problem with that enrich or nutrient-rich strip is farmers cannot go and apply that enrich for entire field. With these spots, we can establish these spots anywhere almost in your field. And so it would be easier and it would be more accurate. So we will have these, we call them biosensor. We use the plants as biosensor. We apply enough nutrient to this spot, and later when we want to apply or we want to check how the plant did with the enough nutrient, we will go back and measure the improvement in this particular spot which we applied the nutrient or nitrogen or any other type of nutrient. So we compare this area with area around it, with the zone we have around it. If we see really good improvement, we consider this one as potential of application. We have potential to apply nutrient here and we will get improvement. For example, here we applied different rate or we apply sufficient rate of nutrient. We don't see any differences. It does mean we don't need any additional nutrient here. Even if we apply, we don't get any result because there is no changes. But here, we apply the same nutrient or any nutrient, and we compare it with around it. If we apply, if we had applied the same rate of nutrient we applied here, we would have got the same result here. So it means with this application, we got this much improvement. So if we had the application here, also we could have that much improvement. So here we will build up an algorithm and we will have equation or recommendation based on our observations. So similar, here we don't see any differences. So it means we don't need to apply. Here we see some differences. So the level of application here would be higher potential to improve, maybe higher potential here, not much, here at all, maybe no, not at all, and so on and so forth. So this is the project we are working on. We want to develop inexpensive wide drop system, and we want to use the growing season, which we cannot go to field and plant. Short growing season in South Dakota makes it so hard to plant after harvesting the corn or soybean. So with this system, we are thinking we can establish the cover crop before harvesting. This is not really new, but we want to make it inexpensive. And also we want to have other conditions. We want to try different methods to maybe coat the seeds and place them there and make them dormant for 2 months. Let's say at planting, you plant the corn seed. We want to these seeds break the dormancy or break the coating around them and take off mid-September. So we want to plant them. This is another part of the project we are working on. Another part of this project is there is a claim that wide drop system has potential to increase the nitrogen use efficiency. And the question from farmers is this scientifically true? And with this research, we want to answer these and similar questions. So impact, we expect, increase the nitrogen use efficiency, increase the yield, and we will work with farmers on farm research on this project. So another project, precision cover cropping system. So when we have different soil variations, we cannot simply have the same seed mix and same seeding rate or flat seeding rate and apply it there. We want to have a logical explanation why we have this seed mix selection and some area why we change the rate. If we can compensate the soil temperature, for example, with seed mix selection or seeding rate, why not? Changing the soil temperature or having impact on soil temperature would help to have uniform stand. And when we have uniform stand, then we will have a uniform need for fertilizer. We will have uniform maturity, and that would be optimum for us, means ideal. So in mixed seed selection or variable seeding rate, variabilities to consider are not only limited to the soil variations. Sometimes topography, when we have north slope, south slope, east slope, west slope, and when we have different phenomena that cause, for example, soil temperature variations, we want to see, can we change our cover crop to compensate the soil temperature? Also, we are talking about the soil compaction. Which cover crops are having more positive effect or impact or improvement on compaction, or means reducing the impact of compaction. So now we know tillage radish and we know cereal rye. Should we go different seeding rate? What's the optimum seeding rate if we have compaction? So these are the questions we want to answer. And one more thing, diseases and pests. If the cover crop is the host for that particular pest, for example, cyst nematode, we should not plant that cover crop in that area. So these are other topics we want to cover. This is what I talked about. We have variation on soil temperature variation that could be because of the slope, north slope, south slope, and we want to address if we can address. As I mentioned, we fly over with the drone. We can collect information related to soil and crop and crop health. So now we are thinking about the NDVI, but it's not only NDVI. We have ongoing projects to introduce more index or indicators than NDVI. We have one instrumented greenhouse. We are working on it. We want to develop a system to generate data set basically when we have crops under stress, different stress or deficiencies of nutrient, then we will have a camera system to watch their behavior while they are under or exposed to the that stress. And we use this one with machine learning and computer training to take this data set and scale it up with a robot or a cart in a field and do the same thing in field. And finally, we want to link it to drones and to the satellite imagery to have machine learning help and artificial intelligence to help us to interpret all of these information which we don't know or we cannot find the interactions cause. So finally, I want to say with cover crops systems, we can use cover crops to mitigate the or eliminate the tillage system. In a state of having tillage, we can have cover crops to reduce the soil compaction, and this is proven by research, supporting by research. I was on these two teams, and these are the measurements from our study. So this is my contact information. Please contact me if you need more information. And thank you very much for your attention. And I'll take your questions if you have.
All right. Well, thank you, Dr. Nafchi. I'll go ahead and have the poll go up. Please answer this if you have a chance to. It helps us to figure out what programming we're going to be doing next. And also watch at the end of the week, you should receive an email with a survey. Please fill that out also, because that will help us figure out our programming for the future and make sure we're addressing all of your needs correctly. And Dr. Nafchi, I'll ask that you stop sharing your screen so I can put the CCA credits up.
Sure.
So if you have any questions, please feel free to put those into the chat. And here is the CCA credit for today's presentation. So if you are looking for that, please feel free to take a picture of that with your phone using your app. But otherwise, thank you again. If there are no questions, I'll leave this up for just a few minutes. But otherwise, thank you again, everyone, for attending.